Well, welcome everyone to the first UNH colloquium of, Space Science colloquium of this year. Today we're excited to have Dr. Michael Terres, who is a postdoctoral fellow at the Harvard and Smithsonian Center for Astrophysics. So before that, Michael received his PhD at the University of Alabama, Huntsville, where he worked with Professor Gang Lee on turbulent energy transfer in the solar wind. So more recently, Michael has turned his attention to kinetic physics and solar wind, which is important for understanding how turbulence is thermalized into heat. So today, Michael will talk to us about reconstructing ion VDFs for insights into solar wind turbulence and wave particle interactions. Thanks, Michael, and take it away.
Yeah, thank you guys for having me. I've met many of you in this room at least once throughout some of our conferences. Others of you, this is our first time getting to meet. So Evan, thank you for the introduction. I am a postdoc who's been working on this reconstruction technique of ion distribution functions for the past 2 years now. It's actually really kind of flown by, but you know, if not more of this work should be attributed to Srijan Das, who's my collaborator on this. We've done so much work together, and I just really wanted to highlight his contribution to the work that we have here today as well. And I hope many of you in the future get a chance to meet him. So part of the motivation for this work, and I think some of this comes down to what I did in my PhD, is I started out looking at turbulence in the solar wind. This is a great way that we can transfer energy down from large scales down to these small kinetic scales. And we started to run into the question of, and issues of, the velocity distribution measurements we have protons have some fundamental limitations, either angular energy resolution issues. For instance, with Parker Solar Probe, one of the issues I'm trying to tackle is that we don't have a full field of view at all times. You know, part of the heat shield will obstruct the distribution function. So we want to try to come up with a way to accurately represent the distribution function, preserve the kinetic features, as well as represent the moments very well. And I list a few of the key open questions that my research has been geared toward. A lot of these are going back down to how turbulence can be transferred from large to small scales, how it's dissipated, what scales those occur at. Not a lot of them will come up in this talk, but most of this is going to stem from the ion distribution function and the kinetic physics. So just as a brief primer, just to review, I don't think you can do any of these talks without introducing the solar wind. The solar wind, you know, that's the sun continually expels a hot plasma that fills throughout the entire interplanetary space. This goes all the way up to the heliopause. And it comes back from predictions of cometary orbits. As a comet would come into the sun, you'd always have a tail radially pointing away from the sun, telling you that there was something that was constantly being expelled out. Parker's famous paper in 1958 that gave the idea of this dynamic solar wind, where you have this constant outflow. And you know, Parker was very, very influential in our field. That's why we do have a current mission that bears his name with Parker Solar Probe. So one of the areas we're particularly interested in is the solar wind itself is generally much hotter. There's some active heating than you'd expect from an adiabatic expansion. So, you know, if you look at the inner heliosphere as well as all the way out to from the Voyager spacecraft, you see this active heating that's occurring. And one way through which we can get this active heating is this turbulent cascade, where large-scale photospheric motions at the surface of the sun, reflection, shear-driven nonlinearities of the solar wind can drive this energy at the injection scale. It'll have cascade down throughout this inertial range in a self-similar way, and then it'll eventually dissipate at kinetic scales. And it's in these kinetic scales that I've spent most of my time recently and trying to understand exactly what's happening. And the way we do that is by actually analyzing the distribution function. So for instance, here I show examples of an ion distribution function. These come from Eckhart Marsh's 2006 review. I think it's a revision to something he posted earlier, and these are all from the Helios observation. And what you can see is that the distribution functions in the solar wind have too few collisions. We're not able to thermalize the distribution. So we're able to get these very highly anisotropic structures in which the cores will have, you know, more temperature perpendicular to the field. We can also get these beam structures or this heat flux that comes in. And all of these dynamics conspire to drive these distributions to different sorts of stability or instability, which is particularly important when we're trying to diagnose and understand what the fundamental physics happen, or what fundamental physics happens at particular locations in the solar wind. Now, all of these parameters are going to depend on different solar wind conditions, such as the plasma beta, Mach number, and things along those lines, which we can touch on a little bit later on. Now, just to go back to those distribution functions, some of these features come up through a lot of these classical resonance conditions. You can have Landau resonance leading to parallel heating, or you get the formation of this heat flux. You can have cyclotron resonance, which leads to these perpendicular contours in space. You can also have non-resonant interactions, such as stochastic heating, which I know some people in this department have spent a lot of time with. And all of these will lead to these massive, or not necessarily massive, but these deformations of the distribution function. And being able to quantify which is happening will tell you what underlying physics is occurring in the system. So I just want to show this here just to again summarize exactly why we're particularly interested in understanding the distribution function. Accurate representations of the distribution allow us to accurately measure the plasma moments. This is very important at the fluid scales. We're looking at the large scale structure of the system. With kinetic structures, we can start to look at the instability versus stability thresholds. There's going to have wave particle resonance. This is how we're going to be able to transfer energy from the waves into the particles, drive these cyclotron-like contours, which are often seen in the solar wind and are a very big active area of research. And ultimately, they're a great place to test a lot of our theory and understanding of kinetic physics within the solar wind. So having these accurate representations are particularly important. Now, just coming back to those of you who may not work with instrumentation, just how do we actually get a 3D measurement of protons or even electrons in the solar wind? One way we do that is through an electrostatic analyzer, and the reason I present these instruments is these are particularly what we use with Parker Solar Probe. We have an electrostatic analyzer that uses deflector plates to deflect ions into the entrance aperture. These ions follow along the radius of curvature to which they're deposited on the anodes. The anodes give you an information about the azimuthal angle or their location in that phase space, and the deflector plates will tell you about the energy or the angular elevation of the particles that are coming in. And if we modulate the overall voltage that goes into the detector, we can get an idea of what energy particles are going to come in, because if the particle has too much energy, it hits the upper plate of the top hat electrostatic analyzer and it's dissipated out. If it's too low, it'll hit the lower plate and it's grounded out. So this is a good way for us to isolate both the energy and angular information for these devices. And then another additional way, and I present this here, and we won't spend a lot of time on this in our talk, but this will come up at the very, very end. We can also use a Faraday cup, which this is actually just a direct measurement of the particles hitting the collector plate. We just measure the total current. And the way we do that is by providing a discriminator voltage, which will select out only ions of a particular energy range. Those will come in. Everything with lower energy is just reflected out. Everything with the proper energy range comes in and hits our detector plate, and we're able to make statistical counts. And this gives us a 1D reduced distribution, whereas the electrostatic analyzers give us the full 3D distribution function. And this will become important when we try to do some of the fitting I'll talk about in the second half. So going back to Parker Solar Probe, the instruments we're going to be talking about here are coming from SPAN A, which has the ion instrument. It also has an electron instrument, and SPAN B is the complementary electron instrument. But since ions are generally much more massive than electrons, they're not nearly as mobile. They're localized to smaller patches in phase space, so we're able to get away with just a single electrostatic analyzer. One of the downsides to that is, Parker is going very close to the sun, so we do need a heat shield to protect all the instrumentation. As such, our 3D electrostatic analyzer measurements often have a heat shield restriction, cutting off part of the distribution function, which can be substantial depending on the radio distance we're at. However, when we're near perihelion, generally the distribution will come into the full field of view, and SPAN is able to give us a very reliable measurement of the plasma moments. Now, when we're a bit further away from perihelion, we're able to use the 1D radial measurement from SPC to come up with the complementary measurement of the overall velocity distribution function. Now, currently, these are two distinct measurements, and the motivation for the work Srijan and I have been doing is to provide and come up with a way that we could actually merge both what the data from SPAN and the data from SPC in a way that treats both properly, taking into account the response functions, and in our case, uses a nice novel distribution basis function to perform these reconstructions. And I'll spend the majority of this talk. Yeah. And I'll spend most of this discussion talking about our first half of making the most of SPAN ion data, where we're going to use our Slepian reconstructions to get to perform our reconstruction. I mentioned a lot there, and I'll touch on that in a little bit more detail as we get through it. So this is just what I was touching on here. This is just a slide to reiterate, how are we able to actually get all these plasma moments, wave interactions if we only have part of the distribution, just to highlight a little bit more of the problem. So the first half of this presentation, I'm going to spend presenting on work that we presented and published earlier this year. We were using observations from Solar Orbiter and OMS, which use very similar electrostatic analyzer designs. However, they are not obstructed by a heat shield. They have full field of view coverage of the ion distribution function. I should caveat that by saying Solar Orbiter does have a unique and distinct angular range you can look at, but 95% of the time, the solar wind population is well within the defined angular resolution of Solar Orbiter. So what we're using, and you may have heard me use this word before, was the Slepian basis function. So I have this fancy picture here of a cat. And what we've defined is a set of orthogonal functions inside this arbitrary domain. And these are known as the Slepian functions. So they can be set up in any arbitrary domain you like. This could be really, really localized. It could be something that's very global. So you could define this over the entirety of a sphere. And in that case, the Slepian basically comes down to a spherical harmonic. So we've all probably worked with spherical harmonics in the past. But a Slepian maintains the orthogonality in an arbitrary domain. It is a real signal. So when we actually take the Fourier transform of it, we get this Hermitian duck signature that comes out of this cat-like signal. And this actually came from one of Srijan's PhD advisors, Frederick Simmons, who was kind of popularized the idea of Slepians in the geophysics community, where you can take the ice mass in Greenland, and you can use that continental shape of Greenland to come up with a Slepian reconstruction and determine different mass loss rates. Recently, this has found adaptations into the solar wind community, well, actually into the solar heliophysics community when we applied this, when Srijan applied this to active regions on the sun. And he's actually currently doing that with stellar active regions, which is really interesting as well, but outside the scope of this work. So we have these localized basis functions that can be defined on any arbitrary domain. And the reason we were particularly interested on them, and I'll show this in a slide or two, is that, as I mentioned before, ions are cold and they're localized in phase space. So we're able to define a domain about a small little patch, and that'll come up in a second. But one thing we really want to talk about is this idea of super resolution. So this is a demo we made a while back, where we took the image from the Event Horizon Telescope of the recent black hole image. It has a really nice high resolution. I think we chose something that was moderately resolved. So this is the 288 by 288 grids. And what we do is we just take this signal and we downsampled it to a 32 by 16 grid. And then what we did from there is we performed a Slepian reconstruction on some localized domain about this distribution. And we came up with this, the model reconstruction, just using those set of basis coefficients. What we're able to do is, because we have basis coefficients defined on the grid, those coefficients do not change. So what we can use is our Slepians on a much higher grid with the same coefficients, and we can see how close to the original image we have. And this is what we refer to as our super resolution. And you can see, if we compare it to the original image, some of the peaks are a little low in comparison, but overall we get the majority of the general structure that's showing up. And now you see here I mentioned about the Nyquist limit. So
is this just a linear interpolation between the low-res grid points?
There is no interpolation. We don't like the term interpolation. So all we've done is we've taken the Slepian function, which is some analytical function that is, it's actually a numerical function, not an analytical function, that is defined previously on this low resolution grid.
Yeah.
And then we have that set of coefficients, and we take that exact numerical recipe that we use to define on that low res grid, and we put it on the high res grid with the low res coefficients. So there is no interpolation that's going on. We're just preserving what data we had originally. And as long as we maintain the wavelengths that are available in that signal, so we don't introduce,
So it's basically a function of, or the difference between the low res and the high res has to do with the specific structures of these functions.
exactly.
That are just pinned at low res points.
Yes, yes. And if we let the Slepians, and this is actually the demo we want to show here, if we let the coefficients that we build have a really high angular variation, so they can have a lot of ripples, what you can see is if you do the same low res mapping, it looks the same, right? The choosing our maximum angular extent of 17 versus 16, they look nearly identical in the low resolution case. But because we've allowed much higher wavelengths into our system, when we use the super resolution fact and what the distribution functions are doing, we add a ton of aliasing into our signal. So this is something we need to be really mindful of when we actually try to use the super resolution fact. But because we know what our instrument grids are defined at, we're able to define our angular resolution that we cannot exceed. So generally, we're able to stay well below this. In practice, there's some test cases that we're trying to make sure we have fully achieved a Nyquist limit and we're not exceeding it. But for the most part, we have a fairly solid grasp of theoretically what we need to define in order to do that. So this gets rid of, there's no linear interpolation, there's no inference of what's going on there. Yeah, I'm glad you asked that though, because that's a big point we want to stress, because
So if you had I know there's other ways of setting up basis functions that have other names.
Yeah.
They would look a little different.
Mm-hmm. Absolutely.
A lot different.
Yes, yeah. So that actually leads into this slide. So this is where we were taking just a localized patch of an ion distribution function from one energy shell of the solar orbiter distribution. So it's localized to the small little region of phase space, as I was saying before, they're relatively cold. If we did the reconstruction, now we're not providing any constraints where it's white in this domain, there's just no data, no counts. So we're not providing any constraints. But what we can do is we can do this reconstruction with spherical harmonics. They are defined globally, so that's over the entire angular space here. Mm-hmm. And what you can see is when you get to 900 spherical harmonics, you're able to actually get a really great representation of that solar orbiter peak. But that comes at the cost of we have some artifacts outside the domain. We can kill those off by enforcing some condition outside the defined data, or we can use our localized basis function that has local support, in which we define a polar cap of the smallest angular degree possible, such that all the data falls in it. And we're able to use 3 Slepian functions to preserve the majority of that structure. And this just goes to show that if we're able to truncate the number of basis functions that we're using to something that's really small, and because we're using solving a linear inverse problem, this reduces the number of matrix operations that have to happen. Because if we only fit 3 basis functions, that's 3 terms going into our linear inversion. We solve for 3 coefficients, and it's much faster than trying to do this with 900.
And part of this improvement comes from actually limiting the space in which these functions Slepian functions are defined.
Exactly. Yes. Yeah. So these are a special case of functions. They are both spatio and spectrally concentrated functions, meaning both in the spatial domain, they obey the arbitrary domain you define, and in the spectral domain, they'll also stay concentrated in that little patch as well. So the fact we have this local support and they follow the variations that are going on in the distribution, we're able to use much less of a fewer number of them to perform just as well as something that goes much higher. Because, for instance, in the past we've used Hermite polynomials or Laguerre, so there's many numbers of expansions that have gone out And part of our reason for comparing this to spherical harmonics was there was work by Adolfo Viñas at Goddard Space Flight Center who was saying spherical harmonics are the natural representation. And unfortunately, when you go to ions, we don't think that's the case. So this just kind of highlights some of the advantages of why we really want to use a Slepian. Thank you for asking those questions. These are what we want. So now I'm just going to give you guys just a little schematic picture of what we're doing. We'll revisit this a couple times. If we're not clear at the end, please make sure I'm explicitly clear on what's going on here. So what we have is just a slice of a instrument frame measurement of a full 3D electrostatic analyzer. So this is something that like MMS can provide. It can give you the full 4 pi steradian ion distribution function from some low energy to some high energy. And I'm just saying we have a measured distribution that's in some localized patch. What we do is we define a polar cap from the instrument origin to the angular extent of that distribution function. And then that polar cap, no matter what the distribution is doing, is where we'll build our Slepians to reproduce the pattern that we have overall in the system. Now, I mentioned that we'll use all the asymmetric basis functions. This will come up a little bit later on the end. We are extending this to gyrotropy, and if we're doing something that's gyrotropic, we need to only use the symmetric ones. But we'll come back to that in a minute. So what this is just kind of showing is this is the 98% of the total density is contained within this polar cap. We do have a couple features that are outside this domain, and what we can do is we can allow a little bit of leakage of our Slepian basis function outside that domain to try to fit those structures. But mainly what we care about is the peak features that are occurring in that energy shell. So we can build the Slepians in that region, and it can be defined for any angular extent that we have in the solar wind. And so this is what we'll generally have. So for one energy slice, we'll have a distribution. We can do our Slepian reconstruction. And then below this, we show the set of Slepian basis functions defined in that polar cap domain that we use to build up this same distribution. Now, there are some general features that are a little bit smoothed out when you look at them closely, but overall, the general features, when you just look at this, are conserved. Now, what I show here at the upper right corner, this is what is referred to as our polar cap localization. This is related to the Shannon number. So we require, now, these are numerical functions at the lowest order. So all of these Slepian functions we show here, 99% of them are contained within the domain you define. However, as you start getting to higher and higher and higher basis functions, you start to get a little bit of leakage outside of that domain. And what we want to do is make sure we truncate that, because if you have all the power outside of the defined domain, it's not going to do anything for your reconstruction other than add some noise. So we do a restriction at the Shannon number, which is defined mathematically. And this allows us to define a well-posed inverse problem, and we're able to do a linear inversion on each of our energy shells using these Slepian coefficients. And what we can see here is if we take an example of 6 different energy shell slices at a single instance in time, you can think of this as we're building the distribution function from lowest energy to highest energy. We can see that overall the general patterns match for every single one of the grids. And what we can then do is we do have to enforce some continuity along the energy direction. And that's where we'll use a B-spline regularization. We can use any sort of function. But all we're saying is that it has to be continuous in energy. With MMS, there might be some things we can do a little bit more advanced. But with Solar Orbiter, we have a lot of really high energy grids. So we're able to get a lot of good high energy fidelity. And it makes that approximation really nice. But what we can do, as I was just mentioning, is you can stack these all together. And you can imagine this is a 3D distribution, and all we've done is just taken a slice through the VZ plane. So we're just slicing this distribution in half. And on the left here, we show what is reported on MMS. Then we do our Slepian reconstruction in the middle here, which is comparing 1 to 1. We see that the peak of the distribution is in the exact same location. These pixel values are roughly the same. And we'll actually refer to this figure in a second to actually look at the pixel by pixel difference of these two images. But then we use the fact that we can use super resolution. So as long as we restrict our basis functions to be within the maximum angular extent, which is defined by the instrument grids. So in this case, we have a Nyquist limit of 16, which comes from, effectively, you have 180 degrees of angular separation, and we have an instrument resolution of, I think, 11.25 or something along those lines. And when you do out the math, you get roughly an L max of 16. So as long as we abide by that, we're able to get a distribution that preserves the low resolution data and now gives us nice smooth gradients without needing the use of any sort of interpolation scheme or approximation there.
And actually, Michael, so how many Slepian coefficients were used for that second panel? Do you roughly, or
for this second panel, these I can't remember it off the top of my head. Were on the order of, I think, like 30 at most.
Okay, just like hundreds, like that.
It's not hundreds, no. I actually think on, if I go back to this slide, this is truncated just before 40.
Okay.
So this basically corresponds to the number of Slepians that we're using. So I think it might be 35 for this case. We've actually done this all the way up to 20, and it's worked pretty well. You do lose, I mean, the number, your truncation order, if you truncate it too early, you will lose some information.
Yeah.
But it really depends on what you're looking for.
Okay.
So for our purposes here, we are trying to preserve as much kinetic structure as we could and argue that we can keep the kinetic features as well as the plasma moments. And that's what we did now. So taking this super resolution data, we now have everything on a nicely defined uniform rectilinear grid that we get to choose. So what we wanted to compare is if we take the moments on this reconstructed high resolution grid and the moments that will be reported from MMS, how well did they agree? And we did this actually for 100 different timestamps over a window. I'll actually have a slide here showing our reconstructions in a second. And we're able to build up these distributions. You have a question?
Yeah, can you go back to one slide?
Absolutely.
Can you explain a little bit about the second bullet point you have? How do you obtain the coefficients from the coefficients?
Yeah. So the coefficients we solve for using the measured MMS data. We have the measured data, and we do a simple linear inverse problem where you say the data equals data minus the Slepian functions times its coefficients is related to your sky. Let me jump ahead, actually. I'm going to jump many slides ahead, sorry. So we go to something like this, right? So you take the log of the distribution function. This is the polar cap, but this is effectively what we're doing. You have a set of coefficients that are applied to your Slepian basis functions. And then what we can do is we can define a cost function. My goodness, I thought I had this cost function already. This is an example, but we can define a cost function, which just comes from chi-squared, which is just your data evaluated on your electrostatic analyzer grid, minus your Slepian basis function times its coefficient. So whenever that value is minimized, which we can solve by doing just a linear inversion. So that's what we call a linear inverse problem. It reduces to the form of something along this, where m sub b is your linear coefficients. You take the transpose of your Slepian coefficients with their actual coefficients, with the electrostatic. You basically just do this matrix multiplication, and you come out with a representation of all your coefficients in one super simple linear inverse problem. This is all coming back to linear algebra. So we solve for these coefficients, m sub b. Once we have those coefficients, we just put those back onto the function here, where we say the log of the distribution function is equal to the coefficients times their basis. And as soon as we do that, we have our reconstructed distribution on the coarse grids. Going back here, I realized I probably should have included that on this slide, but that's exactly where it comes from. So it's a simple linear inverse problem that gets us the coefficients. Once we have the coefficients, we take the Slepians and apply them to a high resolution grid, and we get the super resolved case.
Thanks.
So yeah, no problem. Thanks for asking. Give me just 1 second.
So just a really quick question about
absolutely.
observations, and
Absolutely.
this is the kind of thing that probably observationalists don't want to be asked, but But all this white space on the left
Mhm.
is zero counts, right?
Yes.
And some of this has to do with the instrument
Yeah.
being incapable of measuring in that position.
Of course, yeah. So some of it is we just have zero counts because for whatever reason, the instrument's not getting a count there. And I was talking earlier today with Ben Chandran about this. If you have Poisson noise in the system, and you should generally have one count, it is possible that you measure zero count in that bin,
Sure.
just purely due to the noise associated with it. So
But you know, this funny shape in the center there, is that instrumental?
you're talking about like that lower inner
Yeah,
core?
is that like the instrument is not designed to see that?
Yeah, that's a limitation of the energy resolution. So that's the lowest. So there's an effective circle in this sphere that defines the lowest energy resolution we can get to. And anything below that, we just have
And it's spotty because your color scheme is picking up the one count noise?
Yeah,
Is that?
yeah. So here we have single count noise that leads to all these spotty and spurious
Yeah.
points.
I don't want to take a lot of time.
No. I'm glad you actually brought this up because we actually, in our updated version of this, where we do the gyrotropic case, we allow for your choice of how many counts are what you consider significant.
Mhm.
So you can do this fitting with 10 counts and say you have to have 10 counts to be real, or you can do it with one count and say, okay, we trust one count.
Mhm.
We don't usually trust one count, but for the purpose of this paper, we just wanted to say, hey.
Yeah, it's good to see, you know,
Exactly.
how things,
Yeah.
if things start to look ratty. At some point.
Exactly.
Yeah.
No, and that's why we wanted to test this with, full field of view measurements that are well calibrated, Solar Orbiter and MMS, MMS in particular has spent a ton of time calibrating its ion instrumentation. So we felt really confident. Now, we should probably work a little bit more with the MMS team before we roll this out in a ton of detail, but there's a lot going on there.
Yeah, I just add too, the MMS team does usually provide like the statistical uncertainties for each of the bins. So as you said, you can literally go through and check the count rates and say, okay, well, where's our threshold here? But at least then you can kind of get a sense of if those inner pixels are a little bit more uncertain, you might have a signal there, but you get less certainty to get closer to the zero energy range. But,
exactly. And throughout this paper, I've realized so many more instrumental difficulties that come up that it's opened a whole can of worms. So there's plenty we can touch on there, and we probably should. But the whole highlight that we wanted to show is that over this ensemble where we did our Slepian reconstruction using the high energy, the high resolution distribution, we see that our density is getting us something. I realize these are really small. We get a density on the order of about 98% of the true, at least MMS reported density. We see for the velocity fluctuations, which we expect to be really well constrained, you're looking within 10% of the overall density, even lower for the magnitude of velocity is pretty much 1. We do see a little bit of variation in the temperature, but that's on the order of 30 to 20% at most. So for the most part, we felt we were preserving the statistical moments while getting a nice smooth gradient in phase space, minus the single count points, that we're able to preserve both kinetic structure and the statistical moments. And that's kind of the result we wanted to show. This is just an example, just showing the one of the images I sent over. This is the vertical and horizontal cut planes, kind of demonstrating what the 3D distribution is doing. We just have a single X and Y Cartesian plane cut here on the left. And then we're just showing the statistical moments. So in gold, that kind of faint line there is what was actually reported from our Slepian reconstruction, and the white data is actually the MMS data. And you can see they're following in pretty much lockstep as they go through the range. So this is just to really highlight the robustness of just using our Slepian coefficients with 30 of them, approximately 30 of them. We're able to get really good representation of the moments, and we feel really great representations of the kinetic structure that's going on. We do the same thing with Solar Orbiter. I'm not going to spend a ton of time on this because I actually want to get to the gyrotropic stuff. One thing I do want to point out here is with Solar Orbiter, you do not have a time of flight component to the electrostatic analyzer. What that means is we are not able to separate the alpha from proton populations. So we particularly chose this distribution to reconstruct because this population here is actually representative of the alpha population, and this population here is the proton population. So we were able to just apply the gyrotropic distribution to both populations just to see, hey, does it actually work? Or our Slepian method for this, with using gyrotropic functions, and we're able to get a really good representation here. And then we show the statistical moments. There's a little bit more variability in the solar orbiter densities. But I mean, for the most part, they were falling well within 20% variation. And if you talk to anyone who's making measurements in the solar wind, if you tell me that you get the density measured better than 20% accuracy, they're going to question you very, they're going to be pretty much mad at you if you make that claim. So we felt that the variations were well within the tolerance we'd expect from the instrument. So just showing the pixel by pixel comparison. So what I'm actually doing here, the top panel is the measurement from both solar orbiter and MMS. And what we do is we take our grid resolved Slepian reconstructions on the exact same grids, and we just do a linear difference. And then actually we do a log ratio of the two, sorry. So when you take the log of 1, it goes to 0. And what you can see is that for the majority of the high count points, so where you have the peaks of the distribution, the uncertainties are around 0, meaning you're recovering roughly the same value. As you start to get to those little flanks, those single count points that were popping up, we do see that there's a lot of uncertainty there because we're not resolving them because the Slepian, it's discontinuous. It's not part of the same distribution function. So overall, we were able to see that we were able to preserve the overall structure of the original data. The moments are matching up. And it seems like this is a great method that we can use moving forward. So that's going to lead to the second half of this talk. And this is the work that I've been working on for the past 6 months, every day, just trying to get this working with Srijan. And I think we've actually reached the point where we're happy with the conclusions. William will know each week during our REU seminars, we would talk about our peak and valley of the week. And every week, this project was both my peak and my valley. So I am finally at the point now where this is starting to be just the peak, though writing the paper is still the valley. But so the idea is now we've applied these Slepian basis functions to full field of view coverage. They seem to work great. We can get basis functions probably of any form to do pretty well. But we wanted to say, hey, in the full field of view coverage, we can use a few Slepians, the linear inverse problem, very well posed, works great. Now what happens when we apply this to span? Well, we have part of the data missing due to the heat shield restriction here. So how can we get around that? And that is where we can use the gyrotropic assumption. Now, if you have a distribution that's, if you can resolve these distributions at infinitely high resolution, you can actually find a gyrotropic period. You can find particles bunching. However, when we're looking at the Parker Solar Probe data, the usual accumulation time is about 1.7 to 3.5 seconds. And the actual gyro period is several orders of magnitude higher. That gyro period is the rate at which these particles orbit the background magnetic field. So effectively, when you take a single measurement, any agyrotropic signature you're seeing is being averaged out over that accumulation time. So it's already telling us that the Parker data is already primed for a gyrotropic assumption. So I just wanted to put this in here because someone asked us in our last paper, why would you even consider gyrotropy? And this is the motivation for that. So now that we're trying to do our reconstruction in the gyrotropic frame, we need to convert the distribution into field-aligned coordinates. And what you need to do in order to do that is you need to know what the bulk speed is and what the magnetic field direction is. It's really easy for us to get the magnetic field direction. The fields instrument is really nice. It resolves really high resolution magnetic field measurements, way higher than the cadence that we get from our electrostatic analyzer. One of the problems we run into is if you measure only part of the distribution function, you run into a case where you would take a statistical moment and it would give you something that's exactly on the heat shield. But if we fit this with the Gaussian, you'd see that, hey, maybe the peak of this distribution is actually inside that domain, and it's a little bit lower. So if we have this uncertainty in exactly where the gyrocenter is, or where the actual bulk of this distribution is, as soon as we try to gyrotropize it, we're already lost. We can't do anything better if we can't predict what that gyrocenter is. So this is where Srijan had the brilliant idea to just say, hey, let's run MCMC at it. Let's take our reconstructions, which we can do in the gyrotropic frame. And that would be represented by this black dot and the black data points around it. And then we have a true gyrocenter that's in red that all the data should be gyrotropic about. So if we do our reconstruction, that's at some point way far off from the actual gyrocenter, but we continue to minimize the difference in our data to gyrotropic reconstruction. So if we take all the points in these black circles and subtract from the blue circles, the point at which that's minimized is going to correspond to the point in which we're at least very, very close to that gyrocenter. And what you can notice is in this demonstration that we're showing here is that this method converges really quick within 5 kilometers per second of the actual true gyrocenter. And then over many, many, many more iterations, it slowly converges to the true solution. So that allows us, depending on what type of situation and how accurate we want to be, this allows us to say, okay, if we're within 10% of the velocity, is that good enough? Then we can truncate our MCMC a little bit earlier. If not, we can allow it to run the full resolution and let it converge to a stable solution where we have something that gives us a true gyrocenter. And what this also allows us to do is come up with an uncertainty map of how confident we are that we've actually found the true gyrocenter of this distribution. Now, this isn't perfect. If the distribution is way outside the field of view, we have no shot at actually constraining what's going on because we have to have a certain amount of measurement on the instrument grid.
When you say true gyrocenter, what do you mean? Is that the measured value, or is it?
It should not be the measured value, because if we go back to this measurement here, if you just take the L3 moment and you say, hey, that's our gyrocenter, that's the blue line, that might not truly be indicative of the true gyrocenter. So as soon as we put everything into a gyrotropic frame and say you have to be symmetric, so this point, when you map to your nearest neighbor should be roughly the same. If we keep tweaking that center value, those grids will slightly change, and you'll find a proper configuration in which maybe I didn't explain.
When this red dot, you have a red dot on the next slide. What is that?
So this, So in this example, the red dot is our true gyrocenter.
Measured.
Blue. This would be saying we know.
Hypothetical.
This is our hypothetical. We know it's here. Yeah. And we're slowly taking our data and our reconstruction, which is the black dot, until it converges with the red dot. Yeah. So now, as soon as we get back to this gyrotropic frame, we have an issue that we no longer have this nice symmetry that we were making use of in the previous case. So we have all these mixed up points. You have points in different elevations being mapped next to one another. So it becomes a little difficult to try to do any sort of interpolation, or even some of the spline fittings that'll happen is because you have to make sure you enforce a proper smoothness in order to use these additional functions, and make sure you're not introducing artificial ripples that may be in the system. So we had to come up with a way to adopt our previous method that we had. And this polar cap method is exactly what we presented in the first half, but we had to make one single modification. So I showed this a little bit earlier just to show that we're doing our fittings in log space. We use a set of coefficients, and then we use our Slepians defined over an angular space. Now in this case, we are no longer using the energy grid and the angular resolution on an energy grid to define the Slepian angles. We are using some arbitrary polar cap domain. So what I'm showing here, these black points represent the grids rotated in the gyrotropic frame. We perform an arbitrary shift so that they fall within a cone, and I have a nice little demonstration to show this in a second, so that we can build our Slepians of some angular extent. In this case, we choose angle of 60 degrees for this example that I'm showing here. We build our Slepians, which are represented in this bottom panel in red, that are indicative of the angular extent of the polar cap. And then we say, again, instead of in energy space, we say that we have to have continuity in the parallel direction this time. So now instead of applying the B-splines in the energy space direction, we're applying the B-splines in the parallel direction. And this is just a way to ensure that the distribution maintains having continuity along the parallel direction. And what I can kind of show here is if we follow this red B-spline, that's exactly this red contour point cloud in this distribution of points here. And it's this cloud of points that we are fitting in our linear inverse problem. Instead of a single shell, we now have a little point cloud, which we're just saying that the variation in the radial direction or the B parallel direction has to be basically a B-spline. So another way of visualizing this is we take our distribution, we know that we shifted into the plasma frame, rotate the field aligned coordinates, and all we're saying is we need to make sure that this distribution falls within our cone of influence. And because my office mate loves ice cream, he decided to say ice cream cone, and that's what we stuck with. So you can imagine that this ice cream on top, our distribution, is inside this cone, and we ensure that every single point that meets our count threshold falls in this domain. And as soon as we do that, we're able to use the B-splines and the polar caps to come up with a nice reconstruction. And this is just kind of how we build them up. You can see at the low energy, we can increase all our Slepians and they go through the domain and you kind of build them up throughout the parallel direction. What this allows us to do, and we're going to leverage the same facts as we did before, is we're able to take our span VDF grid. In this case, we did a synthetic model just for demonstration purposes. I'll show actual Parker data in a little bit. We take our original model data, we do our reconstruction on the span grids, and using the same coefficients, and then we use the fact that we have super resolution to take the coefficients that we get from the reconstructed VDF, map them to a 49 by 49 grid, just rectilinear grid, and we're able to get this nice smooth distribution that matches really well to our actual bi-Maxwellian model that we put into the system. Now, there's one point I want to mention here, and this comes down to log versus linear fitting, and we can touch on this at the end. But we do add a set of fiducial points in the center here that serve as a guide to get the amplitude correct for our log fitting. Because you can imagine if you fit in log space, you might have a very small difference at the peak of the distribution. But as soon as you convert to linear space, where we do most of our moment calculations, that blows up. And you can have an order of 200, 300%, or 200 to 300 per cc, so centimeter cubed difference in the overall density, depending on what you're looking at. However, if we just take the nearest points to this peak, so the basically the points in this orange contour, and we do a single little linear single Maxwellian fit to just come up with these fiducial points that just tell us how high it should be if it was a Maxwellian, which the core should generally be collisionally Maxwellian-esque. We can talk about this some. And we just add that as one additional constraint. They actually have no additional weights, nothing changes to them. All they are there is to help constrain where we have no actual measurement along the V parallel direction, just to make sure we can adjust the amplitude. It is not needed. We can remove it, and it will give us a density value that's relatively close. But this is kind of a workaround of the log versus linear fitting that we have to deal with.
Are those points evenly spaced in the V parallel direction? Or
they are evenly spaced in the V parallel direction in log. Right now, we have them, I think, too closely spaced compared to the instrument grid. That's why they look like this little line.
Sure.
But their real contribution to the actual fit is small, other than just getting that little peak. But I mean, they are doing something because they are telling us that the peak needs to be raised a little bit. But again, we can remove those, and our moments will come out, with a systematic error that we can clearly explain, which is log versus linear fit. So one thing that we're able to do is there's this regularization term up in the upper right corner. This comes from the fact that we do enforce some general smoothness We don't want to have sharp gradients in our distribution function because so sometimes if the grids are in strange configurations and you allow it to perfectly fit the data, you might get these little spikes that pop up, but that's not accurate of a true distribution function. So we do a second order smoothness, which is very standard in a numerical fitting. And all we do is vary this mu parameter, and we find it by solving for the L curve of the model versus the data misfit. We can touch back on this in a little bit. We are getting a little late here. I have a few more slides I want to get through. So what I just explained was how we can take the same polar cap method that we did before. We can apply it in this gyrotropic frame, and we can fit all different points. One of the downsides that we have is at the lower energy case, we are conditioned for this distribution to follow a curved arc. So if we have low counts and low energies, it doesn't show up in this model. We can sometimes, in our distribution, get a low energy arc. That would be indicative of some crazy magnetosonic wave or something that's happening in the system that isn't physical that we're enforcing. So this is actually a problem that kept me up and Srijan up for many, many nights. And then we realized that we have this convex hull, which is defined by this white domain, these white dotted points, which represents the area to which the data is constrained. If you guys remember earlier, I mentioned that Slepians are great at defined on arbitrary areas and shapes. So that's where we turn to, let's take that contour and that domain that we have and define our Slepians inside that, just using the Cartesian 2D Slepians that have been defined previously, build them up inside our domain, and solve for those coefficients. And what happens? We're able to get a general resolution that fits the data very well. It matches our model great. The one thing we have to do is we make sure, this is very similar to our maximum angular extent, we make sure that our N2D, which is our Shannon number, that's the amount of ripples that these basis functions can have. As long as they abide by this formula and we don't go too large, we won't introduce any aliasing or artifacts. Now, one problem that you can imagine is this Kmax is defined, this is the effective wavelength or distance from grid points in your domain. Now, you can imagine if we are only measuring the edge of a distribution function, we can get a very large wedge in the center where you don't have data constraining anything here. So you can imagine this first row here, imagine that's just completely gone. And you have very little constraint, you're just measuring the edge of the distribution function, you're gonna have a lot of variation in what Kmax should be. So that there is a bit of a limitation then, you could get the core of the distribution, but you wouldn't have enough constraint, at least in the Cartesian point of view, to recover the beam. So that opened up, we thought we fixed our issue from before, realized we introduced another issue, and that's where we came up with our final method. And this is the hybrid method, and this is kind of where we'll begin to wrap up the talk. So both of these methods so far have been a linear inverse problem. All we do is we solve for the chi-squared difference of the reconstructed values versus the data on the individual grids. And what we're saying now is let's do a joint reconstruction of the polar cap coefficients. So using the Slepians defined on the polar cap, using the B-splines as we defined before, so these two panels. Let's do a reconstruction at the exact same time using the Cartesian coefficients. And then let's enforce that there has to be some similarity on the high resolution grids, not the data grids, but on the high resolution grids, that the polar cap and the Cartesian models have to have some degree of similarity. The reason we want to introduce that similarity is the polar cap method's great at preserving a beam. Cartesian can't get a beam. Polar cap is susceptible to low energy little spikes. Cartesian is not susceptible to that. But if we actually do a joint optimization, solve them in one linear inverse problem, and come up with a general regularization, we're actually able to get a distribution that preserves both the beam and the core of the distribution, not introducing any of those lower energy peaks. And this is just some of the mathematical framework that we can touch on here in a minute. But I want to get through these final test cases just to prove and try to drive home that we're actually able to preserve moments. So we came up with two different test cases. The first case is we take a model by Maxwellian, the same by Maxwellian we've been reconstructing thus far. We rotate the magnetic field and the bulk velocity in a sweeping manner so that the distribution rotates from outside the field of view into the field of view, not really changing in the VZ direction. We're just only changing in the VX, VY plane. And then what we want to compare is the velocity, density, and temperature moments. So looking at the velocity moments in this first half region here, before this red line, this is the entire point in which the distribution is well outside the instrument field of view. We have less than 25% of the total density measured. So you're measuring basically nothing. You have just these really, really, really small flanks that can kind of be seen in the first slide of this video. You're trying to make a measurement from here and constrain your velocity and density and temperature. There's not much that's going on. But we wanted to see how we can do. And there's a lot of variation in the X, Y component and the Z component. Z is relatively fine. You're looking at variations on the order of 10 kilometers per second, which compared to the true magnitude of the velocity is relatively small. The X component, there's a lot of variation depending on which method you look at. Now, I should clarify here, I realized I didn't have it on this slide. The orange curve here is our polar cap method. The blue curve, which is kind of underneath the green curve, is our Cartesian method. And then the hybrid method is in green. That's the one we really want to showcase because that's the one that's actually doing this reconstruction. What is particularly nice is that our MCMC method is able to show that we get larger variation and uncertainties in our VY components when you are in the region that is heat shield obstructed in the Y direction, which is exactly what we expect to happen from our understanding of the observation. Looking at the density, again, we see that our polar cap and hybrid and Cartesian methods all kind of underestimate prior to this vertical red line, which is 25% of the true density. And that's, again, we're only seeing some portion of it. You can't do better than that. You would need some additional measurement or you're not going to be able to get anything more. Now, what's particularly interesting is if you look at the black curve, this is what would happen if you just took the data that's on that instrument grid, did an integration using the normal instrument team integration schemes, and you can see that at this red line, I mentioned it before, this is exactly 25% of the total model distribution is measured. At this point, we are able to get the hybrid, Cartesian, and polar cap density within 95% of the true model density. Now, density, you can say, okay, sure, that's great, but do you actually conserve the actual structure of the distribution? And that's why we go ahead and compute the parallel and perpendicular temperatures. And what we also see is as soon as we reach that threshold, again, our model temperature, parallel temperature, and perpendicular temperatures all come in within 95% of the total density, or the total temperatures that are reported in the model. There is one thing that I do want to point out. There is a systematic variation that comes down to the grids where we get this periodic signature that shows up in the density and the temperature components. This is purely due to the magnetic field coming into alignment with the instrument grids and then coming out of alignment. So you can imagine as you sweep into the grid, you come into alignment with the instrument grid, everything falls back to our previous polar cap method. You get a reconstruction that's absolutely perfect, everything's symmetric. Then you go slightly off, you start to introduce a little bit of numerical errors that come in. So this is a periodic feature that we do know, are aware of, and can clearly explain just due to the systematics and the grids in the system. So again, we do this another test case where you take the magnetic field, you have it anchored at one location. We now take the magnetic field and rotate it throughout the domain just to see what different grid configurations will do to the moment reconstructions. Again, we can see, this looks like a much larger spread compared to what we saw before, but this is actually on a much larger window. We see variations on the order of 2 to 3% in the velocity compared to the actual model velocity. The density stays relatively consistent, well within 10% of the model density. And the same thing holds for the temperature anisotropies, E parallel and T per. So what we wanted to showcase here is that as long as we have 25% of the distribution on our domain, in our synthetic case, in proper configurations, we believe we can get you a decent representation of the distribution function. Now, we're never going to have an ideal case in the solar wind, as we'll come back to in a few slides. But generally, our hybrid method, polar cap method, and Cartesian method, all three work. There are some general limitations, but this is kind of the result that we wanted to showcase for our synthetic case. I'm going to jump through just quickly an example comparing the span-I observations, where we actually applied our polar cap method to the span-I observation, compared to a bi-Maxwellian fit of the span-I observation. What you can see at the low energy count here is that little curvature feature, which comes in due to the polar cap fitting. This completely goes away when we do the hybrid fit. But what we really want to focus on is in the positive portion of V parallel here, is you can see that the bi-Maxwellian fit just has this single small heat flux feature that comes in, whereas our actual polar cap distribution, when you actually treat the data properly, gives you a much larger signature. Perhaps we could have something that looks like a cyclotron resonance or something along those lines. So these are features that we want to investigate and look at in some more detail. And just to showcase, the application, we've applied this to actual Parker data with our recent hybrid variations. And this is just updating in time, showing that we're able to conserve our moments for the temperature. We are calculating temperature and isotropy because that's for another study we're trying to do. And we just really wanted to showcase the robustness of this method. So I'm going to go a little bit over time just to go, I'm not going to go through this, but I want to showcase this in a little bit of detail, because those of you who are interested, hopefully I've been able to convince you that we have a cool, interesting tool. It is open source. It is readily available. We do have a GitHub repo. You are welcome to download it, use it. It is the latest version. We do have to do some updates to the documentation, but we've written this in such a way that you don't really have to do too much. You just have to specify. You can take what we already predefined, or you can specify, the choice of different models. So I just wanted to run through quickly what our configuration file is. We have our global parameters where we go through and we can say which method do we want to use. Do we want to use the hybrid method, the Cartesian, our polar cap method? How well do they work? We can choose whatever time range from Parker Solar Probe data. We are working to get Solar Orbiter and MMS in the same pipeline. You can pass it a synthetic data file. You can do choose the number of timestamps you want to look at, all these different features. You can pass it if you want to use, if you're part of the instrument team, you can pass whatever instrument credentials you may have. You can also choose, what your count mask threshold is. Phil, going back to your question earlier, of what points are significant. You can choose something on the order of 10 or 2 or 0, whatever you would like to choose. You can save the figures, the output files. The save super resolution saves the super resolved grids, which would be something particularly useful for like ALPS or a dispersion relationship solver that needs these nice uniform grids. We can choose our number of points. We can choose if we want to use our MCMC method. And then we have our 3 constraints that, depending on what model you want to use, you have an angular extent choice that you can hard code yourself. So if you want to just find a polar cap that's a maximum angle of 60 degrees, you can do that, or you can let it be variable. And these are all things that are calculated on the back end, and it's all open source, readily available. We really want people to try to use this tool. We feel like we have a hammer and we're looking for a bunch of nails to start applying this to. And yeah, I'll conclude my talk there because I am going a little bit over the hour here. But I'm open for many questions. I'll stick around for a little bit. And yeah, thank you guys for your attention. Yeah, there's a lot to go over there, and I went over a lot really fast. So I'm sorry.
I was wondering, when you set up the original basis of these functions, there are probably some free parameters that you can choose. For instance, the domain that you choose, and perhaps the number of the functions, maybe there are others.
Yeah.
So how do the final results depend on on your choice of the free parameter? Do you have a sense
Yeah.
of that? And
Yeah.
is it like instructions how to do that?
Yeah, so that's actually something we've spent a ton of time trying to figure out. So originally, when we would set up the polar cap, for instance, we'll just talk about polar cap. Same thing would go for Cartesian, but when we originally would set this polar cap up, you had a choice of what your theta was going to be. You had a choice of what your B-spline polynomial was going to be. You had many little hyperparameters you could tune. We have now made it to the point where there are very few hyperparameters that you tune. There's only one thing that you can set. For instance, in polar cap, if you set an angular extent of theta, we are so this theta, the maximum angle. As soon as you set that one hyperparameter, all other hyperparameters in the system are updated based on that. And what those are the going back to the Shannon number that I discussed. I kind of briefly showed it here on this slide, this N2D cart. We also have an N pole cap. And based off of the initial conditions that you have, and the fact that our grid has to have a 15-degree angular resolution between grid points, right? That's what the instrument tells us the variation is. We update all the hyperparameters for there. So we have spent a lot of time, and in our current paper, we have a lot of detail explaining exactly, how we set these hyperparameters to be just one term instead of being something that has a lot of variability. Because that, I mean, you can imagine, any something fitting, it can become a nightmare of which one do I actually choose.
Yeah, but also how the results, if I choose something slightly different,
Yes.
will the results be also slightly different, or maybe they be a lot?
Yeah, so we ran into that issue early on when we were doing this. That was one of the issues, that if we chose a polar cap angle of 60 degrees or 30 degrees, our final result of the distribution would be absolutely ridiculous. One of the issues that we were able to resolve was the fact that if you change your polar cap, the maximum allowable information in your angular width changes with the angle you define your polar cap to be. So if we enforce that you can only have this much information, and you choose some arbitrary polar cap, it's now a self-consistent check to make sure you're always abiding by the instrument resolution. So that's something we are making a hard-coded requirement.
And that's in the code too.
Yes, that's all in the back end. We'll have this all written up in detail, and we're happy to talk about this in a lot more detail. I mean, I'm sure as we go through and people are using this, they might come up with questions that we didn't initially think of. Because I mean, it's kind of hard to do all of that while you're developing the package.
Yeah, when it's in the wild, it's whole different.
Exactly. We expect once we have the public release, it's going to be a bunch of edge cases that we didn't consider to begin with. So, but no, we're really happy to get this started. For me, I'm really excited to have nice smooth gradients in phase space, so I can start applying all these differential operators in phase space and start seeing what happens and compare to some theories. So we'll see what the results can be. But we're excited about the future of this. So yeah, great question. I'm glad you brought it up. Yeah.
I'm also interested in the slip-in reconstruction.
Okay.
So you have maybe 30-something slip-in coefficients.
Mhm.
And you also have probably a lot more bins in your data than that.
Yes.
And am I correct that that makes this an overdetermined problem? Linear inversion?
Yeah.
So if that's true, how did you feel that?
I don't believe it's necessarily overdetermined, and you're asking the wrong person in this. Unfortunately, I'm the bronze, so to say, where I just attack the data. Srijan's on. Hey, Srijan, do you want to answer that question for us?
Yeah, can you hear me?
If not, we can repeat it.
Can you hear me?
I don't know. Is there any other? Maybe you can unmute.
Am I audible? Can you hear me?
Try again.
Can you hear me now?
Yes,
I can hear a little bit.
but
Okay.
on my speaker, not
Okay.
that speaker for some reason.
Okay.
Go ahead.
Okay, so no, it is an overdetermined problem, just like if you have 100 points and if you're trying to fit a straight line through it, you have two parameters and you would want it to be overdetermined because there is noise in your system. If your system was perfectly noise-free, you could choose exactly the same number of coefficients or parameters as your data and you would have a perfect answer. But because your data is not perfect, you would want it to be as overdetermined as possible. So that's the answer. Yeah.
Yeah, thank you. And sort of as a follow-up question to that, some of your bins probably have higher uncertainty than others. Like, for example, in the center or near the center, there are some bins that you said were probably from noise, or some of the bins that are almost black that have very few counts. Did you do anything in the inversion to account for the fact that some of the bins probably matter less?
I'm going to start with that real quick, Sri John. We, in the current fitting method, there's nothing that's going to take into account count space.
Okay.
We have developed an entire framework that is going to take into account the response function of the instrument.
Okay.
And that will be able to also account for the counts.
Great.
But the only thing we do right now is a count threshold. But Srijan, if you want to add to that, feel free.
No, I think that's basically the answer. We are perfectly set up to include a data covariance matrix, which is where your noise is going to go in. It's just one more term in the linear inverse problem. Yeah.
Thank you, Luke.
Yeah.
Thanks for asking. Great questions. And you can see some of my shakiness with some of the linear inversion stuff. Because I haven't worked with it as well.
All right, well, if there are no more questions, let's thank the speaker again.